Hi, I'm Mason Lin, and today we're going to talk about volumes of revolution. Okay, so we have a 3D structure right here. So this structure, as you can see, is this triangle on the XY plane, rotated around the x-axis, all the way around to form a cone. So now let's break down the triangle and see how we can find the volume. So here you see I've made this into 4 cylinders. So now we know how to find the volume of cylinders. So right here, this cylinder, these 4 cylinders would be volume of equals limit x to 4. So right, this formula, we can see this is accounting for the area of one slice with one slice of area of one single cylinder. Then x is just basically distance from here to here. So then we can find the volume of the entire cylinder. Now this would add up 1, 2, 3, 4 of these cylinders to create a volume that's kind of close to a cone. However, if we want to be exact, since this is pretty inaccurate, we can go ahead and make, instead of 4 cylinders, make infinite amount of cylinders. So that will be limit as x goes to infinity, sum of all the areas, that would be the radius times width. So that is the way we can find it. But however, since we've already done integrals, we know that is, if we see this as a single function, we can break it down into the integral of a to b, and if we put the pi in front, we know that will be the same as this, since we've already learned about integrals. Now we will have 5 different situations that we will counter. However, every single one of them, if you break it down enough, they're just basically the same formula right here in various forms. So let's see all 5 these situations. So the first one we've already seen is basically area under a straight line or a curve. However, the second one, it's the area between 2 functions, rotated around so that there's a hollow on the middle. Now, third one is rotating instead of around the x-axis on a different point. So this is probably negative something, negative. And then this area right here, rotated around to form a ring. Now right here, we have something that is rotated around the y-axis instead of the x-axis. So this area right here, rotated around to form a cup. And right here, there's 2 different functions that enclose the area that we're rotating. So this entire area, rotate around to form a gyro, yes. Alright, so the first one, let's take a look at y equals x squared plus 1 in the interval 0 to 1. It'll look something like this. So from 0 to 1. That's the area we're rotating. And so the volume would be the radius of that rotated around the x-axis to form a shape like this. And from what we learned, we wouldn't put it in as pi times 0 to 1 times the radius, which is x cubed plus 1 squared d of x. Now, distributing the power of 2 into the addition, we would get x to the 9th power times 2 x squared plus 1 d of x pi. And solving the integral, we would take the derivative of this function, which will be x to the 10th over 10 plus 2x to the 4th over 4 plus x squared. Remember, from the interval 0 to 1. And just to simplify the function down, and now dividing by plugging x in, subtract by plugging 0 in, but plugging 0 in would all be equal to 0 because we have x on the top in every single part. So that will be 1 over 10 plus 1/2 plus 1, which we will get 27 over 20. Remember, units squared. And there you have the volume of this structure. Okay, now time for this one. So let's have the region between y equals x plus 2 and y equals x squared. So x squared would look something like this, and x plus 2 would look something like this. Now we want this area where the regions enclose a certain area. Now these 2 points are points of intersection between the 2 functions. So, and that is the interval in which the area is at. And so we have to find the intersects by setting these 2 functions equal to each other and factoring it out. Now we get x equals 2 and x equals -1. These 2 are our intercepts. This is -1 and this is 2. So now if we look at the structure of this thing, it looks something like that, with everything in the middle hollowed out, everything that's not of the shaded region spun around the x-axis. So how we find it is basically solving for the larger volume, which would be this right here, which is x plus 2, spin it around the x-axis to form a solid structure. Now we subtract the inside, which is the area under this curve, which is y equals x squared, spun around the x-axis. So that would be the pi times -1 to 2 times x plus 2, which is the longer radius, squared d of x subtracted by the inside part, which we are hollowing out. Now, for this case, and every other case where we do this kind of problem, we can write this in a more compact form, which is just the longer radius, which will be always higher in terms of value than the smaller radius of x squared. It's the shorter radius, smaller value. And that is all that. And basically now we solve the function. And taking the integral, which would mean the antiderivative, and the interval of -1 to 2. Basically simplifying that down. And plugging that in, which will give you a lot of numbers, but it'll give you 87 over 15 pi unit squared. Now let's look at the situation, which is about this one, rotating around an alternative axis. So let's have y equals x squared, and rotate it about y equals -1. Around there. So area under y equals x squared, rotated around this axis. It'll look something like this, kind of. Now, this is kind of similar to the other one where we had two functions. This is basically, what we basically do is change the radius a bit. This radius, instead of being just the function itself right here, we have right here. Now that is going to be the larger radius. Now, the smaller radius would just be the distance between the axis and the x-axis. So that would be obviously 1. Now, using those radiuses, we can plug it in. That will be +1 squared. Now, solving that like any other integral problem, we'll get the answer for 6 over 15 pi unit cubed. Now let's look at the fourth situation where we rotate around the y-axis, which is a vertical axis. So let's set the region between y equals x squared and x equals 4, y equals 4. And the y-axis, which is x equals 0. This area rotated around x equals, and that would be something like this. That is hollowed out. Now, rotating in terms of a y vertical axis with x value of something, well, it's basically the same as rotating around a y equals something axis, except everything is in terms of y. So the radius is in terms of y. The outer radius right here is, I'll take the x and convert it to in terms of y. So now that represents this part of the radius, and the whole radius would just be square root of y plus 1, kind for this part. So that would be the larger radius, and we would take 0, since this is 4, we'll take 0 to 4. This is y equals 0, this is y equals 4. See, it's the same thing as if you were rotating around the axis. You're taking the interval right here, subtracted by this inner radius, which we're hollowing out, which is 1 squared. All in terms of y, remember, it's in terms of y. Now, solving all of that, as you would solve any other integral, and you would get 68 over 3 times pi units cubed. The last situation is when we have two different functions enclosing the area. So into this case, we have y equals x squared and y equals -x plus 2. Area enclosed between them and the x-axis. So since there's two separate functions enclosing this area, we can't really do it under one interval. So we're going to separate these two into two different intervals, just like how we would separate something into piecewise functions. So the first one, we have to look at the intercepts of the two functions, which would be calculated by setting them equal to each other, which is these two are the intercepts. However, we see that it's going to be positive, so this is going to be at 1, and the end of this interval will be the x-intercept of that value will be 2. So now let's look at the two different areas rotated about the x-axis. So the first one right here is going to be pi times 0 to 1 interval of the function right here, which is going to be x squared. And square that in terms of x, and adding on to the second half of the interval, which would be 1 to 2, and the radius would be negative x plus 2 square the radius in terms of fx. Now, you cannot combine these two like how you combine the area between two different functions rotating around an axis, because there's different intervals in this case. Now, solving all of that separately, you would get 1/5 pi plus 1/3 pi, and that would add up to become 8/15 units cubed. That covers all 5 different situations right here. And that's all you need to know to solve volumes of rotation.